So we basically got this field structure. That's an S1 mode, and now this is different view angles. Basically, we have one polarity. It's the radial field component always. Basically, one polarity on one hemisphere and the other on the opposite hemisphere. And it's practically impossible to get anything else with any reasonable choice of parameter. This specific electromotive force, basically the S1 will always be the first excited mode, so it's very hard to get something else. And that's of course also not an oscillating mode. This type of dynamo is always stationary except for a slight rotation. But okay, that's the way it is. That's what we get from this sort of model. So what do observers actually see? This is a recent observation by Donati et al. Collaboration using Doppler-Zeeman imaging, and these field lines here are potential field extrapolations. And this is for a low mass star, B374P, which is fully convective, at least according to theory. We can look into the star, of course. And what we see is basically an axisymmetric dipole. So not quite what we expected from this alpha square model. You see these are field maps here. It isn't quite axisymmetric, but roughly it is basically a dipole. What's also comes out of this work is a measurement of the differential rotation, which says basically it's small but solar type. This number here is basically 1/10 in this unit, 1/10 of the solar differential rotation. So there is some, but it's weak. Okay, so let's first try, is there some alpha square dynamo that can produce this field structure? The alpha effect as computed by the second order correlation approximation obviously won't do it. This is simulation. So what do simulations tell us? This is from a simulation by Ossendreiber et al. 2002, which basically, not quite confirmed with Soka. They confirmed the second order correlation approximation insofar as they found an anisotropy, so the horizontal components are basically identical, but the Z component is different. This was carried out at the South Pole, I think, so Z is the rotation axis again. What one can also see is there are some sign changes here. So it's a bit complicated structure. Okay, can one do something with this type of alpha effect? I'll change this one. Yeah, see, the answer is one can. So let's try all field polarities and look which one is the first that's excited. So this is just the A1 mode. This just shows the geometry, which has very strong concentration of the field at the poles, basically. The same is essentially true for the S1, but it's not quite so high latitudes. It's a bit lower. But basically, it's all very high latitudes. The same here. And this is S0. I probably should have brought this first, because this shows the alpha effect that was actually used. Here were we have two types of alpha here. One is homogeneous but anisotropic, and one is inhomogeneous and also anisotropic. And the bottom, the diffusion is anisotropic too, which is a result of the second order correlation approximation. And this is actually known to help axisymmetry. And we will see that here too. These are lowest critical Reynolds number for all these modes I showed, and this for various parameters of the anisotropy. Basically, in the diffusion, what we can see is that for this, for these types of alpha 0, as from the Soka, we always get the S1, that was the old result basically. If one takes something like the opposite of the horizontal alpha, then this is the same. There's something in between here. Yes, for strongly anisotropic diffusion, one can produce this here. And with this alpha profiles as shown here, where the alpha z actually changes the sign here in the middle of the convection zone. Here one actually has some cases where one can get this the A0 mode as the first excited mode. That's also an excited, it goes directly from the S1 to the A0. None of the others is ever the lowest excited mode. So with this model, one can get this this axisymmetric field from from pure alpha square dynamo, but it does look, yeah, well, it is a very specific setup, let's say this one. So what about differential rotation? This observation of B37174 said it's small, but well, it's still there. So why not try alpha omega dynamo? So what can we tell about differential rotation from theory? We have a relatively successful model there for differential rotation. It's based on the same mean field approach as dynamo theory, which however seems to look better than for dynamo, in that we actually get quite close to the observations. The analog to the alpha effect, so to speak, is basically here the lambda effect. So in this case, instead of electromotive force, we have an additional stress tensor, the Reynolds stress, and that has two parts, viscous and non-viscous, and this is proportional to the rotation rate, so this will actually derive differential rotation. Okay, and there's our theory for that too. And one can basically play the same game. And this is the result, which is actually very nice. This is the observed profile again from helioseismology. That's what we get out of the model, which contains rotation, meridional flow, and heat transport. And what we see here for is that the correspondence is very nice actually. It's basically the same. And that's remarkable because there isn't all that much space for parameter tuning and so on. So one cannot make any model fit.
This is a theory of differential rotation which was developed in the papers by Rudiger and Chettina.
Basically the same, yes.
Yeah.
Okay. This is meridional flow. We see it's basically also the same order of magnitude. Values are actually quite close. Bottom convection zone, bottom flow at the bottom of the convection zone can't be observed, of course, but this model says it's about half or 1/3 of the flow at the top of the convection zone. Now, what does that help us for the M stars? Well, observers have over the last couple of years focused on the dependence of surface shear on temperature. In the 90s there has been a number of work where people sought dependence on the rotation period itself, which worked to some degree as long as the range wasn't too big, but if you do that over a whole range of rotation period, it has actually observed it doesn't look all that good. If you do this versus temperature, it looks not so bad. This is from Barnes et al. Who derived this T to the 9th law. One has to be a bit careful because error bars are large and the scatter is very large and the sun isn't quite on the curve, but I think the trend is clear. It's something one shouldn't just discount. This is the same law basically, but with some hotter stars added to rotation. Our model gets basically the same dependence. It's not. It doesn't have this steep decline towards low temperatures. This is model calculation. This is again the T to the 9th law. This is a sequence here showing basically differential rotation as a function of rotation period different spectral types, so it goes down here. So we would expect it to be weak for M stars, but not zero. That's the important point. Oops. Somehow. That's this one. Something else. Oh yeah, here we are. So the result we get from this model for the M star, this is 0.3 solar masses, so it's from an actual model that was made to fit the observational parameters for the star. We get something like this. This structure here is artificial because there's a hole here. Rotation is basically solar type, but you get this very thin boundary layer here, and what's of course the important part is here the value of the rotation period of the shear, which is quite by a factor of 5 or so larger than what was observed. But we are also a factor of 10 still away from the rotation period that's observed. The star is a very fast rotator, and we don't quite reach that for a number of reasons. Now, if we put this rotation pattern into an alpha square or an omega dynamo, then of course we can play the same game again. And we can basically, oops. So this is the S1 mode. This is the model for no differential rotation. So this is the DS1 mode again. Alpha effect is from SOPA again now. So, and if we vary Coriolis number and this the rotation period essentially, then we can basically produce everything here. This is again the field structures, which looks different, practically similar than before. We have these antisymmetric or symmetric surface fields. This is quadrupolar and dipolar axisymmetric. One important difference, of course, is that these are now oscillating. Okay. So that's an important difference between this model and the alpha square dynamo. The axisymmetric modes here oscillate. Okay. Now, which mode actually is the most easily excited? Sometimes is can depend very delicately on the parameters, as we see right here. The only difference between these two runs is the diffusion in the outer parts. In one case, it was just 10 times the diffusion in the star itself. Here, it was 100 times, which would be closer to vacuum. And what we see here is, in one case, we have dipolar solution, and here we have an even solution. It's quadrupolar, but axisymmetric in both cases. So, yeah, there is no good, it's still a bit confusing, but what we can say is with an alpha omega dynamo, one can produce, of course, axisymmetric dipoles, but of course, depending on how strong the rotation is, all sorts of other modes too. So, yeah, this point by point. Observations for this one star for which we saw this image shows the strong axisymmetric dipole, which isn't something we would have expected before from this mean field dynamo. Differential rotation is weak, but there, so there is room for an alpha omega dynamo. Yeah, both work. If you choose the right setup, you can produce a dipolar solution with an alpha square dynamo, but of course you can also do it with an alpha omega. The interesting thing will of course be if they do monitoring of that star, does it oscillate or not. And what we haven't talked about at all here is the meridional flow, which should play some role actually. Okay, that's fine. Thank you. No, not really. No.
So it was the a posteriori, it wasn't a prediction.
It was a posteriori.
If I remember correctly, it's not prediction, but it is before was observation after that. But my question now, what kind of population have you done? Is this non-linear population in sense of magnetic field?
Yeah, non-linear but kinematic. So
What does it mean, non-linear but kinematic?
it's just some alpha tension.
You mean just equation function, nothing else? No,
Yeah.
no Stokes equation at all.
No, in the dynamo model it's not. That's just kinematic.
More questions? So when you had the S0 mode with an anisotropic alpha, but of course a little bit of shear would turn it immediately into an A0 mode. And it is quite likely that at least these rapidly rotating Vittori stars that you showed by Donati do have a little bit of shear at least.
Yeah, that's
That
essentially
may be well sufficient.
what I did here.
So you would agree with that?
Yeah, definitely. But of course, the shear wasn't very strong, which they found. So if one believes that, of course, that sets a limit to, basically to the diffusion coefficient to get the right C omega.
And there's the same problem with the planets, of course, with Saturn in particular.
That was basically the idea to find out.
For your diffusion tensor, you use the anisotropic form,
Yes.
and you use some coefficient value from 0 to 2.
Yeah.
And I mean, for this size, which number to choose?
Pardon?
I mean, what is the most physically relevant number to use for H? You just vary some impedance and waste.
Well, that's basically what comes out of this soccer models that predict that basically. Right?
Should it depend on the rotation? But you cannot really fix the values. You cannot fix the strength of the anisotrope.
Pardon?
I mean, from your theory, you can predict H. Never at parallel equal to H at T.
Yeah.
So, do you know the form of H from your theory?
Yeah, yes.
Then why did you put from 0 to 2 in your simulation?
I mean, there must be some misunderstanding perhaps. I mean, all you're saying is, I guess, that the alpha effect must have some contribution from the differential rotation. And the tensorial form is clearly of this form. And the coefficient in front of this, these are unit vectors, must have something to do with this. And so if it's maximally, I mean, in that case, it's replaced by omega, of course, it says. And of course, if it's maximally helical, then the coefficient in front of this must be unity.
Yeah, but what she was asking was something else.
If you have a 2, then this is because they have a positive omega. You just ask something else?
You're asking for eta. Right? Eta, not alpha. Or beta, whatever.
Yes, but it's a prediction from theory that for fast rotation it's twice as strong in the z direction than the first. And this was just varied to study the effect, how important it is.
Okay. Any more questions? Then before we sync, let's say 4 o'clock or what do you think? 25 minutes? Yeah. Okay, 4 o'clock for the coffee. Thank you.
Thank you. Several speakers have expressed their gratitude for being invited here. But, yeah, I know, mine goes blank. But I have a special thanks to give because if I weren't giving this talk at this precise moment, I would be in a telethon concerning budget plans. So, thank you very much. I am so grateful. Okay, so the organizers suggested this title, and it's a lovely title, except that, as you will see, It's going to be only partly honest as a title. I think the contents will be as honest as I can make them. And I should thank in particular my student Dmitry Shapovalov, who is spending his time back in Canada right now, where the weather is almost the same, so it really doesn't make any difference. Okay, this is a very general talk. What is a non-helical dynamo? Actually, don't like this term a whole lot because it's meant to refer to dispensing with any discussion of kinetic helicity, but I'm going to be talking about dynamo effects that have a lot to do with magnetic helicity. So this is a helical dynamo in some sense. And my interest in the topic, and I think the interest of other people who work in this field, including several people in this room, was driven by the realization, which for me dawned somewhere in the late 1990s, that in a very high conductivity fluid, if you try to drive a dynamo by putting in kinetic helicity, the way we were all taught when we were much younger, except for those of you who have never been much younger than you are now, of course. The kinetic helicity turns off at a fairly low level, or let's say the dynamo process turns in at a fairly low level, a process called alpha quenching. And when I first heard about it, I thought to myself, this has got to be completely wrong. And then eventually it occurred to me that, in fact, it was irrefutable, so that made me think about it. Okay, so what are the dynamics here? This is all stuff that should be achingly familiar to people. We have the induction equation with large-scale flows and large-scale magnetic fields and small-scale flows and small-scale magnetic fields. And I'm doing a kind of two-scale approximation where I break things in this way. You can make this rigorous by imposing a filtering method that just calls this everything that's not included in this, but that's less enlightening, although more correct. And then the question is, how do you evaluate this thing? And one particularly nice way is that if you don't know what it is, you might suppose that it starts out at 0 at some arbitrary moment, and you let the turbulence evolve for any time, and you can calculate its time gradient at the initial moment, and then just multiply that by a correlation time. And if you do this, you get the usual expression after you throw out terms here which involve pressure gradients, and I'm going to throw them out also. You get something that looks like this, where this thing is what's usually been used in mean field dynamo theory, and this is something that usually hasn't. Now, the physical significance of those two terms, the first one has to do with the twistiness of the velocity field. And if you take the trace, you find that that first term becomes the kinetic helicity, v dot omega. And the second term is the current helicity, j dot b. Neither of these is a conserved quantity in MHD, and so, again, at very early times, people just assumed that you could dictate them by some kind of special forcing, and that is true for the kinetic helicity, but there's a problem with trying to play with the current helicity in this way, which is to say that the magnetic helicity, vector potential dot b, is a robustly conserved quantity in MHD. It is so incredibly interesting as a conserved quantity. It's even seen to be more or less conserved, or at least to evolve more slowly than the energy in laboratory experiments, which compared to astrophysical objects, a lot of resistivity. The reason for the relatively robust status of this as a conserved quantity is, well, you can think about it dimensionally. It's got the dimensions of a length scale times an energy density. So if you imagine taking a given amount of magnetic helicity and stuffing it down into small scale structures where it could be annihilated by some finite amount of resistivity, or even an infinitesimal amount of resistivity, you have the problem that as you go to small length scales, the energy density has to blow up. So if you have any appreciable amount of magnetic helicity in the system, you can't transfer it to small scales at any with the available energy, and therefore it will stick around in the system. Okay, so this thing is a robustly conserved quantity. However, unfortunately, it's a gauge-dependent quantity, which makes it kind of nasty to work with. The physical effects that we're concerned about all relate actually to the current helicity. But I like working with conserved quantities, and so the answer is that you try to pick a gauge choice such that there's more or less a local correspondence between this thing, which is a non-local quantity, and this thing, which is a physically measurable local quantity. And so, although dictating that you're using a Coulomb gauge and saying A vanishes at infinity does it for you, the simplest thing to note is just that this is the expression that works for that choice, and it's manifestly obvious that if you take the dot product of this with B, then you have a certain degree of non-locality, but features in J that are on small scales will be correlated with B on the same scale. And of course, that definition of A is a perfectly simple one to implement. So you have this robustly conserved quantity. It's related to something that appears in the dynamo equation. And so what does that tell you? Well, there's another step to think about here, which is that you can break up the magnetic helicity into a large-scale piece and a small-scale piece. These are both, in some sense, large-scale pieces. They refer to a large-scale distribution of magnetic helicity. But this comes from small-scale structures, and this comes from large-scale structures. The sum of the two is conserved. Either one of them is not. So you can write down a pair of equations. This thing, time derivative of this, is the divergence of a current, plus the term that represents the transfer between big H and little h. And of course, this just has to have the negative transfer term, and then its own current representing all the pieces of the magnetic helicity current, which is not included in this. Okay? This is a complicated flux. All I'm going to say about it is that it consists of two pieces, one of which is trivial, just a velocity times the magnetic helicity, and the other non-trivial piece, which is the difference between this piece, this is the electrostatic potential, and a contribution from here, corresponds to, if you think about a rope, finite thickness, you can either move magnetic helicity along because a spiraling of the rope travels down the rope, or you can just take the rope in your hand and rotate it, and you will generate spirals with opposite sign moving in opposite directions. So that's a local generation of a helicity flux. This kind of effect, taking a rope and twisting it like this, okay, is something that's obviously physically doable without moving the boundaries. If you think about the way dynamo theory is usually expressed in a cartoon way, you take a rope and you twist it into a spiral without moving the boundaries, which is a much harder thing to do. In fact, you have to have some sort of complicated local counter-twisting, and basically the fact that it doesn't work is why this is a conserved quantity, this topological thing. Okay, so the fact that this is the transfer term is what makes life interesting. Because what it says is magnetic helicity, current helicity actually, contributes to this thing. And this thing also describes the transfer of magnetic helicity between scales. So if you run a dynamo by imposing some u cross b from any source at all, then you separate out magnetic helicity of opposite signs, large scale and small scale. The small scale magnetic helicity, the little h that you pull up, represents a counterforce. It will try to turn off u cross b. So regardless of the source that you use to drive this, you get alpha quenching from the back reaction from little h. And that sets in early, before you've done very much to your Lloyd scale field. Very much is a context-dependent statement, but certainly well before you reach any kind of equipartition with the turbulence. Okay. For very weak fields, we're in a regime where we can still use kinematic dynamo theory, but that doesn't get us to equipartition. It's not all that interesting for actual applications, so we need to think about how to do this for stronger fields where this is an important effect. So one of the simplest things to do is simply say, okay, the transfer of little h between scales is something that occurs rapidly. As you approach equipartition, it occurs on an eddy turnover time. That's much shorter than a dynamo time. So let's just set this derivative equal to 0. And then, ignoring resistive terms, this thing is equal to minus the divergence of this flux, whatever this flux might be. Okay? And I see Professor Cleorin nodding his head because he thought about this a while ago. The real question is then, how do you evaluate this, and does it give you any kind of reasonable dynamo effect? Now, mind you, this is only directly constraining the component of the electromotive force parallel to the magnetic field, but that's the piece that actually contributes to the dynamo. The piece perpendicular to it just moves magnetic field around. Okay, so there are various steps you can take here. One is to sit down and calculate H in some paradigm, doing a quasi-linear calculation from a particular kind of instability, for example, or as a general analysis of moments. And I'm going to leave that alone for a second. I just want to make some general comments, what you expect to find. Okay. First of all, this is a trivial piece. If you think about what the magnetic helicity flux looks like, it looks like the magnetic helicity times a velocity. So it's got 2 powers of the magnetic field, and then a distance, and then a velocity. So you don't expect it to switch sign when you switch the sign of the magnetic field, for example. It's going to go with some even powers of a large scale field. Okay, so that's one point. Second point is, if you do a complete parity transformation, it shouldn't change sign there either. It's got even powers of distance built into it. So it actually should be robust even under conditions that a normal dynamo you get by imposing kinetic helicity shouldn't work. Of course, it's got to be 0 for isotropic turbulence. It doesn't know what direction to go in that case. The term that we calculated in my paper on this topic, which is not the only term by any means, it's the simplest term to think about, involves taking let's say a bundle of magnetic field lines. You imagine the turbulence twists any field line into a mixture of right and left-handed spirals. But along the field line, nothing has changed once you average over the field line. So that manifestly conserves magnetic helicity. Then you break the spirals and move the right-handed ones in one direction, the left-handed ones in another direction. And that still conserves magnetic helicity. You just have to believe in magnetic reconnection, which is a matter of faith, so I put it that way. And then if you have a gradient in the strength of the field or the strength of the spirals anyhow, and you reconnect your spiral segments, you will end up in general with field lines with a net sense of spiraling. That's a step which kinetic helicity does by fiat, which is to say, as it turns out, ineffectively. So that term sounds very obscure and complicated, but it turns out that it's actually easy to do. You expect something like this to arise in, say, a differentially rotating turbulent fluid. You don't necessarily expect a dynamo, but you expect some magnetic helicity flows. So it's a fairly general point. Well, if you have a differentially rotating system, that cries out for the alpha omega dynamo. And so I'm thinking in terms of the simple cylindrical geometry here. The magnetic helicity flux should be something like this. It's got to have some constant of order unity out front whose sign you don't know a priori. It's got the vertical diffusion coefficient. Dimensionally, it's got to be like a diffusion coefficient, a velocity times a distance. And it's the vertical because you're actually trying to move this in the vertical direction to get a successful dynamo. And because it doesn't depend on the sign of vertical distances, it's got to go as a velocity squared. So it's the vertical velocity squared that comes in here. And then in the absence of differential rotation, you wouldn't have anything. So you have to have some equivalent of the Rossby number. And here I put it in for a slow rotator. So here we're weakly, I'm sorry, yes, a slow rotator. So this is some small number which represents the anisotropy and the turbulence induced by the differential rotation.
This is result of derivation, or you wrote this is by symmetry reasoning?
This is by symmetry reasoning.
Okay.
I should say that if you calculate out the terms for slow rotation, you get a bunch of terms which all look like this.
Mhm.
And I did that first, so I can't claim any deep insight by applying symmetries, okay? I have to be honest here. Okay, so simple alpha omega dynamo. So you're generating the azimuthal field by some kind of shear, and you're generating the radial field by some alpha effect, and if you plug in this formula for the alpha, the formula for the alpha effect, this is what you get. And it looks like a funny kind of diffusion equation. And depending on the sign of this F, it can either represent diffusion or a kind of anti-diffusion. Okay. So, whether you get a dynamo from this or an anti-dynamo, well, whether you get a dynamo or not obviously depends on the strength of the dissipator terms, which I haven't written down. Whether you get a dynamo out of this or an anti-dynamo, something that shuts off the magnetic field, depends on the sign of F. Okay, and it can go either way. If F has the wrong sign, then the growth rate you get is imaginary, the dissipative terms function without competition, and everything goes away. If you just think about this in terms of a simple periodic box, and real astrophysical objects have all kinds of complications, but let's ignore that for a second. The dynamo grows only if F times this derivative is negative. So for example, if you have an accretion disk where the rotational velocity drops as you go outward radially, then that says that magnetic helicity flux goes towards your north pole along your spin axis. If the angular velocity increases radially in a system, then magnetic helicity flux is anti-parallel to the spin axis for a successful dynamo. Now, let me just pause to say something here. One of the interesting things about this is that it says that if you imagine a disk dynamo, you can think of it as a machine for, either transferring magnetic helicity through the disk or, more physically, reasonably, ejecting positive magnetic helicity on one side and negative on the other. This is a kind of environmental pollution, okay, due to accretion disks or stars or galaxies, that is coherent over time, even if the dynamo does polarity reversals, because nothing about this depends on the polarity of the dynamo. So if you have a disk with a lot of separate angular magnetic domains, it'll still be doing this. If a star has cycles and flips like our sun every 11 years, the sense in which it is ejecting helicity into its environment is the same at all times.
Sorry, I have a question. You said that dynamo grows, there is a dynamo growth only if the sign of this term is negative. Is it implied that saturated level of the magnetic field is very low? Or you haven't observed any growth of the magnetic field in the case of shear flow?
Oh, no. One of the characteristics, I'll get to this in a second, but this is not a limit on what the dynamo can do. I guess I forgot to write down that point. In this simple model, if you look at the total magnetic helicity current, it is simply going from one side of the disk to another. But some of the time, as it's traveling, it's contained in small-scale structures, and some of the time it's contained in large-scale structures. And since I was looking at a periodic box, I didn't really care where you put the boundaries. So you're not making magnetic helicity, you're not creating it out of thin air. You're, in effect, like in an accretion disk, you're rejecting positive magnetic helicity from the top in some form. Doesn't care for the formalism whether it's large-scale structures or small-scale structures. You're rejecting magnetic helicity with a negative sign from the bottom of the disk. Again, it doesn't depend on whether you're rejecting some big spiral waves or lots of individual twisted up bubbles. It works equally well. It takes a lot less energy just to put out big spiraling waves, of course. And so, I think I lost a slide. Well, so the basic point is that the dynamo has to have a way of ejecting magnetic helicity from the system, but it doesn't care about the form of the magnetic helicity, whether it's large or small, and it doesn't ever reach the point where an accumulation of magnetic helicity of one kind or another is a problem. You can just keep going. Okay, so the way I wrote these equations, it looks like a linear equation that hides some nonlinearities, but you get a growth rate which looks something like this. A vertical eddy extent divided by a vertical domain times the shear rate gives you the growth rate, which is a pretty boring answer, and it looks a lot like standard kinematic dynamo prediction. I should add that if this is as big as this, then the same kind of simple estimates give you a turbulent diffusion rate, which is as big as the dynamo growth rate. Now, there's a funny thing that happens. Saturation is often assumed just to happen by fiat when the magnetic field becomes strong compared to the underlying turbulence, or as strong as. It's assumed that other terms come in. This particular model has its own saturation mechanism built into the terms already being used here. Basically, once the magnetic field gets stronger than the equipartition level, so that the Alfvén speed is greater than the turbulent velocity, it becomes harder to bend the magnetic field lines. And this growth rate starts to drop because the vertical extent of individual motions starts to drop. And I said something earlier, speaking partly to I said something earlier to Kandu, which I realized is not quite right. What saturation this corresponds to is somewhat model dependent. There are various ways of getting the answer depending on where you think the dissipative mechanisms are coming from. But one answer that actually works a bit better than the one I gave Kandu, and I'm sorry, is that you get a saturation value of the Alfvén velocity, which is some sort of funny mean between the mean square velocity and the vertical height of magnetic field domains and the local shear. And in practice, this tells you that in general, your saturation value is a bit super equipartition. For the galactic disk, it's mildly so, you would say. For most systems, it's sort of mildly so. I don't think that seeing super equipartition magnetic fields tells you the MRI is involved. I know the MRI does this, and people often invoke it when they see a super equipartition value, but I don't think there's any necessary conclusion there. Oh, here's the slide I should have put earlier. So, okay, so this is what I already said, that magnetic helicity is flowing through the system. It's partly contained in the flow of big H, and it's partly contained in the flow of little h. And the sum is a constant. And opposite signs of magnetic helicity are ejected from opposite signs of the system, which is what we see in the sun. Because of the nature of magnetic helicity, it's energetically cheaper to put a certain amount of twistiness into very big structures as opposed to very little structures. But even if you imagine that all the magnetic helicity is being ejected as very little structures, the energy involved to do this is some fraction of the energy that goes into generating the magnetic field. This does tell you, of course, that a dynamo simulation is going to be very sensitive to vertical boundary conditions, because if you set them up so the magnetic helicity can't cross the boundaries, they'll throttle the whole process. Okay, so, right. So we don't have to inject kinetic helicity to get a dynamo. Boundary conditions are a problem. The simplest way, which of course the universe doesn't have accessible to it, is to use periodic boundary conditions in a computational box. The universe has to solve the problem of actually injecting magnetic helicity. This kind of simple analysis tells you that large-scale shear plus turbulence gives you a dynamo or an antidynamo. It doesn't tell you which. But if you play with the properties of the turbulence in the system, you ought to be able to get even. Okay, so I have a student doing this. I say we, it's the royal we, of course. Dimitri ran simulations with a periodic box with a small explicit resistivity and viscosity, posed a sinusoidal shear through a steady jet lag, steady forcing. And he used a Rossby number about 1, which means that the energy involved in that large-scale shear is much greater than the energy in the small-scale turbulence. We explicitly set the kinetic helicity forcing equal to 0, just to make life simple. And we put in a seed field with 0 net flux and filtered the forcing to get different ellipsoids in k-space. And how do we do? Well, we're still checking the results. But it looks like we have found dynamos and we found antidynamos. The dynamos, the couple of simulations that I've seen from him do saturate actually slightly above equipartition. We see sort of 4 regimes in the way things go. Put in a Weeks field, you've got turbulence, you get this initial very rapid growth in magnetic energy just because the eddies are wrapping things up. You get the generation of a long wavelength tail out to the size of the box from basically incoherent dynamo effects. All the different eddies add a little bit of different electromotive force to the box as a whole, and you generate a tail, which should be roughly Poisson in the radial field bit. Then we think we're seeing a large-scale dynamo regime for FUE foldings. And then the thing saturates and it sort of bounces around, but doesn't go away. That's for the dynamo. But this is the other thing that can happen. This is time equals 0, and this is wave number 0. And this, although this looks like a mountain, this is the small initial field strength on the large sinusoidal pattern. And we turn things on with basically very small kz compared to the other components of the k vectors and the forcing. And we turn the dynamo off. So you see, initially there was some response on the turbulence scale, but even that died away. So if there are stars in the universe with absolutely no magnetic fields, we know how to produce them.
Yeah, so these simulations with strong shear in the sense that shear multiplied by the correlation time of the order of unity, yes? Okay.
So this is strong shear.
Yeah.
And that's, of course, not so much like the galactic disk, but it's very much like, say, an MRI instability in an accretion disk. Now, here's the embarrassing thing. I know I've seen simulations with a successful dynamo, but my student said he'd send me the file with a graph just as pretty as this, and then he didn't do so. So if I were sitting out in the audience listening to this, I would have a certain amount of skepticism that we've really seen a dynamo. But that's okay. I'm a little skeptical too. We will see what we will see. And that's the end of the talk. With a little comment about experiment.
Could you read this first big question?
You can ask me questions, the other people can read it.
Yeah, I was intrigued by the comment that you can have this helicity flux in the small scales or large scales. Because the different equations, then the form of the helicity flux is completely different for the, let's say, the mean field and the small scale field. So, I mean, how does it work from equations?
Well, course, since there's perfect conservation of magnetic helicity, there are really only two ways that you can simply get a solution, right? You could either have that the small-scale magnetic helicity flux is going this way whenever the large-scale magnetic helicity flux is going this way. And then at any one point, you have zero magnetic helicity flux totally, but you could still set up a cycle where it moves this way, cascades to large scales, moves this way, and is canceled by opposite sign coming from small scales, or equivalently, well, anyhow, you get the idea. But I couldn't find a solution like that. The equations seem to always demand that the two of them, in a simple alpha omega dynamo, had to be going in the same direction. And I don't know if there's a profound reason for that. But given that they were going in the same direction, they have to add up to a constant. So they have to trade off between one another.
Okay. In principle, magnetic helicity business and magnetic helicity flux is very important for saturation of large-scale magnetic field. Of course, it is enough not very strong magnetic field in order to have strong influence of magnetic helicity. Yeah? But for pure generation of magnetic field is responsible other mechanism, not magnetic helicity. Magnetic helicity is strongly responsible for saturated level of the magnetic field. This is the first, this is my opinion. Yeah. And the second, I think it's not so important the form of the flux of magnetic helicity. Very important is to have not small flux of magnetic helicity. But the form of flux, okay, it can change details, but in order to have saturated field on the level of equipartition,
I think that's basically true. I mean, the reason I wrote down this generic form was because I thought it's not only what you can deduce more or less from symmetry, but it's all you really need to know to discuss the problem. So implicitly, I guess I must be agreeing with you.
Okay.
And I certainly agree with you on the first one. I think, if you have a sufficiently weak magnetic field, and you can forget about magnetic helicity flux, you can just treat it like a kinematic dynamo problem.
In general, I agree with you and with Igor, but I would like to make some comment. If you, first of all, what kind of magnetic Reynolds number have you got in your system? I mean, which based on the
infinite.
Yeah.
What?
Implicitly, I'm taking infinite, but if you mean the simulations.
Yes, in the simulation.
In the simulations, it depends how you define it, but for what we've done so far, not very impressive, on the order of a few hundred.
Which based on the scale of Box.
Mm-hmm.
And what is scale separation?
We've taken the turbulent forcing is about k equals 10.
Yeah.
So on the scale of the turbulence itself is not all that realistic. It's just realistic enough that magnetic helicity conservation looks good.
Nice. But it means that your magnetic Reynolds number for small scale of the order of maximum 10.
Tens, but
maybe less.
I'm not going to argue.
But it's not. But what's important? All this business about magnetic helicity conservation important just with the Reynolds number enough large. If not, you have got normal ohmic diffusion, which give you totally another process.
I agree. And of course, one of the things we've checked and continue to check is whether or not our magnetic helicity conservation looks good enough. Is that term small compared to everything else that's going on?
You mean that the dissipation is really small?
I mean, we can explicitly see the extent to which magnetic helicity conservation is satisfied, and it's not infinitesimal, but it is at least an order of magnitude smaller than everything else that's going on.
Conservation is true just when Reynolds number tends to something enough large. 10 is not large.
It appears to be large enough. That's all I can say. Obviously, better is better, and we're going to be doing more tests at higher resolution. But
Okay.
This business of magnetic helicity constellation I never really understood. I mean, it's always put the energy
But you're not actually violating magneticity conservation in that problem.
No, but whatever it's doing to the magnetic elasticity is doing just as efficiently as it's doing to the energy.
But you're not. But the constraint is on what happens to the total magnetic elasticity. That evolves slowly. In the case of the kinematic dynamo process, the magnetic elasticity actually, in its original form, the magnetic elasticity isn't changing at all. It's zero at all times.
No, it's not at all. Not at all. No.
Yeah, because you're
That's
generating.
Not true. No, that's not true. It's not true. If you start...
You're just generating the scale
that's-
separation.
No, that's not true. If you start with... I'll tell you one. It's a famous dynamo by Galloway and Proctor, for example. You can start wherever you want. You can start with a with a magnetic elasticity. You can start with whatever you want. It will find its eigenfunction. The eigenfunction has non-zero magnetic elasticity, and it grows exponentially, and because it's an eigenfunction, it grows exponentially.
Violates a conservation law.
Yeah, but it's not conserved.
There is a conservation law.
It's not conserved because you've got diffusion, but you've always got diffusion. But you're saying, oh well, I've almost got a conservation law. That's the point. And I'm saying, why don't you almost have a conservation law for a kinematic dynamo?
Because you can turn. Oh, I see what you're saying. Well, I'm not sure I see what you're saying. For a simple kinematic dynamo, you should either you have. I'm sorry. Any fast dynamo that remains true as the resistivity goes to zero. I simply don't believe you can end up with a net magnetic elasticity.
No, I don't think resistivity goes to zero in this case, right? You must be generating through the resistive term, I guess.
Yeah.
Of course, of course.
Right.
But an arbitrarily small resistive term. And they're not different. If you look at them, you can't. They're both growing exponentially. And they're both non-zero.
The only way you can do that is if you make sure that the magnetic spectrum is tilted so that you have large amounts of non-conservation of magnetic elasticity on very small scales.
Yeah, that's
Which is it's not a turbulent spectrum.
Well,
Like,
that's-
imagine you can set it up by hand, but you don't expect it to happen in real life.
In thermal regime, you've got realizability condition, which organize this strange behavior of magnetic elasticity. It's true.
So
It's not strange. You come up with any... Right down the old kinematic fast dynamo. And of
But
course, by
kinematic fast
definition...
dynamo is not this dynamo. It's not kinematic in some sense. It's dynamic.
No, but I mean, there's a legitimate question here.
The-
There are terms which do not conserve magnetic elasticity, just as in turbulence there are terms which do not conserve energy, right? And in turbulence, I mean, all of turbulence is driven basically by the cascade of energy to small scales where it's annihilated. Given a MHD turbulent cascade, there's not enough energy at small scales to contain the energy you would need to annihilate magnetic elasticity. So I'm not sure what example you're quoting here, and I would have to look and see, but it must have some large amount of energy at some arbitrarily small scale to do this. I'm sure it must. Sure it must.
It's an elliptical flow which acts as a fast dynamo. But the eigenfunction of a fast dynamo does not have zero magnetic elasticity.
Okay, look, I'm going to have to see this example. I disbelieve it completely, but we can stand here and toss words back and forth all the time. But you can't make the argument.
Can not magnetic helical process. It's for definition. Magnetic elasticity is non-linear, non-linear phenomenon in general.
No, it's not. It's a definition. It's an interval of A and B.
can I try to do a stupid chairman summary of this debate? So this is correct that magnetic helicity has to be destroyed through a resistive process, which which goes with some unfortunate power, so that it should be usually low. So a small hole for we have a bass tube full of helicity, and we drill a small hole into it through which helicity can flow out. Now the debate is about, is this very natural for the water to find, or for the helicity to find its escape? And you're claiming that it's very natural that the helicity finds its way out, and you're saying no, it's...
No.
Is this roughly the
I
debate?
think that's a fair statement. I mean, obviously there is a resolution to this argument beyond the Monty Python sketch, but...
Okay, I'm
This was a short question.
The dynamo effect you described, it's essentially non-linear, right?
Yes.
Can it kick off from very weak magnetic field? Probably not, right? You need something to amplify magnetic field for this to start working.
Whether this, I mean, this needs a very small magnetic field could conceivably be run this way, but it would be unlikely to be run this way. The process becomes sharply inefficient at the point where the magnetic helicity does not transfer between scales rapidly, which is the basic assumption I'm making here. And saying that the magnetic field moves efficiently between scales is essentially saying that there is sufficient large-scale magnetic field so that an efficient coherent reaction is possible. In the absence of that, you would get, if you were moving magnetic helicity around, you would get a local cascading K space toward larger scales. But if there were any kind of kinematic dynamo operating, it ought to win. Exactly where this process would take over from a kinematic dynamo does depend on physical circumstances, but I would generically expect a kinematic dynamo to be important in small amplitudes.
Okay. Thank you.
This is where technology meets the barbarian. Thank you very much.
I could, of course, ask Ethan my question anyway.
You're the organizer.
Or I would rather rephrase the statement in a slightly other sense. So, in the traditional viewpoint, we have the kinematic alpha effect. In addition to this, we have the magnetic contribution. The magnetic contribution obeys a conservation law, and this conservation law has the divergence term, of course, in it, and that's exactly the term that drives, in your case, the dynamo. So, in the and this, of course, is a bit unusual because, in the traditional sense, it is the kinematic alpha which begins to drive it, and then the only reason why we have and why the magnetic part is important is in order to quench this. So in your case, you are actually running your dynamo based on quenching alone.
Yes.
And so that is an entirely nonlinear phenomenon, and that does require a finite threshold, clearly. And Kandu and I looked at this in 2005 in a paper that I can show later, where we determined where this threshold lies. And we also found that the amplitude that is required for this to work, you wrote down the expression in non-dimensional form, but there's a non-dimensional parameter in front of this, which we don't know very well from the theory or from numerics. And if this parameter is larger than 0.6, which you need to verify numerically, then this self-excited dynamo based on the divergence of the flux would work on its own. If not, then it would not. But it would still act as an exhaust valve to get rid of magnetic helicity that is being generated through the usual alpha effect. Okay, these are just the same things in different words. And I hope in the meantime Mike gets ready.
That worked.
Good start.
Okay, thank you very much. Can somebody hear me, or is it too loud? So, as I'm moving immediately to the next pane here. We've heard a lot about the alpha effect, and we've also heard a lot about its organisation. So if I run out of time, or rather run out of things to say before the time ends, I'm sure that you won't be sad. I'm also very sorry that the green, halfway down the page, seems to be the same colour as the black, the back thing, so you won't be able to read it. I can't read it either, so I'll tell you what it says, more or less. Anyway, we remind ourselves of the alpha ansatz, which is very well known. I don't have to explain it in any detail to you. I just write up there a couple of equations. Now, is there a pointer thing, Eugene?
Yes.
Yeah.
This thing?
Yes.
And how do I do it without killing me? Oh, I see, like that. Okay.
Experimental.
The essence of this, of course, is to produce a mean. This is the induction equation with a mean EMF, and the mean EMF is calculated from the velocity average, and in principle one can calculate this EMF from this rather difficult equation here with a small-scale fluctuating field. And we typically understand the alpha effect to arise due to helicity in small-scale turbulence. And if the turbulence is not helical, modulo the talk we've just heard, then if it has reflection symmetric statistics, we don't expect an alpha effect here. And if we want to have large-scale dynamo action from small-scale flows of that kind, then perhaps we have to rely on rather more complicated ways of writing the EMF instead of this very simple local expression without any derivatives in B. If it's present and it's well defined, it really exists, then it leads to dynamo action on small enough scales. Now there's a question, of course, is what happens if there is a small-scale dynamo, fluctuation dynamo as some people call it. That is a difficult question which I don't intend to answer today. This says, I'll tell you what it says. I don't understand why it looks fine on this screen. It's called, what's that called? It's called teal, I think, this colour. I'm sorry, I won't use teal again. Other mean field effects, for example, the omega cross J effect of regular, are not guaranteed as the new term has the same number of derivatives of the diffusive term. So the alpha effect term is different because it has fewer derivatives than diffusion. So at long enough scales you can ignore diffusion, and the alpha effect will lead to dynamo action on the largest scale if it exists. However, as we all know, when you do numerical calculations, and we've seen this today, it's very hard to fit numerical calculations into a simple formalism. There are large fluctuations in EMF, and I'm going to show a copy of what David showed earlier. And the interesting thing is that even in non-helical flows, we have to remember that the EMF itself, this quantity here, can fluctuate even about zero with large non-zero fluctuations. Oh, how do I go back? Back there, is it?
Yes.
So this reprises what David said. Rotating convection. Here is an example of what they did. They have a layer of fluid heated from below. Gravity is vertical, unless that's a tautology. And so is the rotation axis. It's boosted inertia fluid. You get vigorous convection with lots of helicity. So if you plotted the helicity, you would get, as he showed, a very well-defined helicity. However, if you apply a uniform field to this problem, and you measure the space-averaged EMF in the top half of the layer, you get a signal with very small mean, but very large fluctuations. And you can see there are three directions of the EMF here. The applied field is, I believe, in the x direction, but you wouldn't know it from this sequence of plots. So you might as well say that these are fluctuating essentially about zero mean. And if there is a mean, the fluctuations are much larger than the mean. And indeed, you don't see any, in this particular simulation, you don't see any large-scale field at all, because the alpha effect is so feeble. Now, it may be that you'll never see any large-scale effect, even if you have shearing of a coherent sort, as was discussed this morning. But I'm going to soldier on anyway in the hope that at some level we can make something of this.